Through how to solve a non-orthogonal river problem, and I think you might be able to figure it. You probably can figure it out on your own, but just in case, I want to be as careful as I can be about teaching you everything you need to know. So right now, the reason I'm putting the little picture of myself right there. Oh, I forgot to join my own Google Meet. Let's see who all's there. Hey, Luke. Of course, Luke's there. Hey, Luke. Uh-oh. I need to fix your volume. Speakers. Digital output. It works. Hey, Luke, will you say something so I can make sure we hear you?
Hello.
We're good.
Hello. Okay.
Oh, okay. So I was telling everybody, the reason I'm recording this today is because on my bullet points, which are very tiny, the second thing down is questions about the test. And if somebody's not here and they're just thinking they can just do what's in Google Classroom, I want to at least have this there for them. But before we get to questions about the test, I want to do this warm-up, which I've already got a video of explaining it, but I think I might be able to do a little bit better, and it's probably better live because then you can ask questions. So this is a river problem like the ones you've been working on, but it's non-orthogonal. So it's not like anything's going straight across the river northward and the river's flowing eastward. It's things at funny angles. So we've got to do a little different approach. Then after that, anybody who has questions about the homework, that'd be the time to ask those. And then we'll talk about the test. These are just steps I tried to type out very prescribed procedure for solving a non-orthogonal river problem. You may not need this. I mean, don't feel like you ever have to follow any steps that I give you. If you know how to do it your own way, don't even bother with this. But that's just there because a lot of people had trouble last term. Hey. Okay, thanks for letting me know, Aruna. All right, so, let's see, I need to, what do I need to do? Find my mouse. My mouse is hidden. I'm going to freeze this. Hey, Claire. Oh, yes, you should be able to see what we're doing. Thank you. And feel free to blurt that out. I might have not even looked at the chat thing. All right. Good. Freezing that. Switching to the camera. So now people at home can see this. All right. So we've got the golf cart on an aircraft carrier. See my nice photoshopping? Pretty good, except for the fact that that's the size of a jet, and that's the size of the golf cart, so maybe not so good. So there's a golf cart on an aircraft carrier, and it's traveling with a velocity of 4 meters per second in a direction 32 degrees west of north, relative to the Earth. So if you had some kind of tracker on that golf cart, and you were looking at it from like Google Earth, you would see it go, moving across your map in exactly that direction at exactly that speed. If the aircraft carrier's velocity is 6 meters per second in a direction 10 degrees east of north, so again, if you were tracking the aircraft carrier, you'd see it going this fast, and instead of so west of north, 32 degrees is like this. That's the way the golf cart's moving. 10 degrees east of north, that's the way the aircraft carrier is moving. What are the golf cart's heading and speedometer reading? So, in other words, if the person driving the golf cart had a compass and was reading off so many degrees this way, that way, and following that compass reading, what would that compass reading be? Like, which direction is the person on the golf cart trying to head? And what would the speedometer say? So how many meters per second is it actually traveling across the deck of the aircraft carrier? So this is the hardest kind of river problem, and it's the hardest way to give you the hardest kind of river problem. And what's that? Yeah, it's all of the hardest So here are my steps for doing this. Identify the vectors, including the given vectors and the unknown vector that you're trying to find. So we've got 3 vectors. Oh, by the way, people at home, get your calculators out too, because I'm going to call on people to do my calculations for me. I'll call on somebody to do a calculation, then I'll call on our next person to confirm the calculation. And I've got to get into physics. Ooh, term 2 physics, not term 1 physics. Ooh, it has trouble saying Riam. Sorry about that. You don't have to do anything yet, Riam. So, what?
I thought you said my last name.
Oh. Ooh, no. It's just first names. So the I'll find the three vectors. There's this 4 meters per second in a direction 32 degrees west of north. So just for now, I'm just going to connect it. This is one of the vectors. This is the direction, and this is the magnitude. No, sorry. This is the magnitude. This is the direction. And then the other one is the aircraft carrier's velocity, 6 meters per second, 10 degrees east of north. So that's the second vector. And then the third one, this is the unknown, the golf cart's heading and speedometer reading. So that's the one we don't know. And I should be writing these down, but I'll write them down in a minute. That's the first step. Just identify all the vectors. There could be 4 or 5 or 6. There could be 7 or 8 different forces that are combining to give you one force in the end, or 7 or 8 velocities. Now we could say all this is happening on the Earth, and the Earth is spinning this way so fast. And the Earth is also revolving around the sun this other way at such a speed, and we could add all those up. But that's just too much for practice. Why do that? So now identify the resultant vector. Somebody tell me, of these 3, which one's the resultant vector? It's not the heading and speedometer reading. So we've got 2 choices now. Is it the 4 meters per second, 32 degrees west of north, or 6 meters per second, 10 degrees? It's not that one. It's this one. So there's, in all these problems, there's going to be, I haven't found a succinct way to describe it, but there's just the star of the problem, really. The object, the main character in this, really is the golf cart. We're trying to figure out which way the what the golf cart's doing, and what the golf cart's doing is being complicated by the fact that the aircraft carrier is moving underneath it. But the resultant is always going to be the velocity of the object that's the main character in this relative to the Earth. So that's this. 4 meters per second, 32 degrees west of north. I kind of want to put it in a table now, but I'll just write it. 4 meters per second, 32 degrees west of north. This is the resultant. This is the golf cart velocity relative to the Earth. So it's going to be something's velocity relative to the Earth. In this case, it's not the aircraft carrier's velocity relative to the Earth, because the golf cart's heading and speed is going to have no bearing on the movement of the aircraft carrier. The movement of the aircraft carrier plus the way the golf cart's trying to go, those two are going to add up to the golf cart moving like it does. So that's the resultant vector. And then the 2 components are going to be the unknown. So that's the cart heading and speed. Or it's not really the speed. I'm just going to call it the speedometer reading. One thing that I sometimes spend a lot of time on but haven't really talked about in here is the idea of airspeed with an airplane. And if you watched one of my videos, that I made accessible to you. I talked about that. So airspeed, if you have an airplane, is the speed of the airplane relative to the air. So there's airspeed and there's ground speed. Ground speed is the actual velocity relative to the ground below. But if you have a plane that the speedometer says 100 miles per hour, and that's your airspeed, but at the same time the wind is blowing 100 miles per hour into your face, how fast is the plane actually going relative to the ground? Zero. It's just hovering there. So that's the difference between the airspeed, which is how fast it would travel through still air, and ground speed, which is how fast it's actually traveling relative to the earth. So this golf cart speedometer reading, that doesn't really tell you how fast the golf cart's moving across the earth. If the aircraft carrier is going this way and the golf cart's sitting on top of the aircraft carrier going the other way, then it might not be moving at all relative to the earth. But the speedometer is still going to say it's doing something. So that's never going to be, a speedometer reading, unless you're on the ground, on the earth, isn't going to be the actual velocity relative to the earth. And then the other component, that's the aircraft carrier. So aircraft carrier velocity, which is 6 meters per second, 10 degrees east of north. And now I can get rid of all this irritating stuff on here and actually solve the problem. So the next step, oops, I think what I should do, I'm going to move this over on my other screen and maybe I can see it and the people there so I can see my other steps. But now I can't see them. Oh well. Maybe I'll just go back and forth. So somebody watching this video could, now I've lost my other people. I'm sorry. You all think I'm crazy. You can't see any of this happening. So my next step is to resolve all the given vectors into their x and y components. And then after that, I'm going to make a table. So here we go. So I've got, let me just draw these separately. This, I'm going to draw 4 meters per second, 32 degrees west of north. Doesn't matter if I draw this correctly. This is north. This is west of north, right here. So this is 32 degrees, and this is 4 meters per second. And I need to find the x and y components of that. That's the golf cart velocity relative to the earth. That's the way it's actually moving. And another one I'm going to have to do, I'll just put it over here, is this one. I can't do anything about this because I don't have any numbers. The aircraft carrier velocity is 6 meters per second, 10 degrees east of north. So if this is north, 10 degrees east of north is like this. And this is 6 meters per second. So I've got to get the x and y components. Now this is where I'm going to need people to do some calculating. For this vector, oh sorry, this is the y component and this is the x component. I'd like somebody to calculate that y component there. And I'll, if this is 32 degrees, I'll do a little formula for it. So I can say the cosine, cosine of 32 degrees equals Vy, or sorry, Vx. Did I call this the, no, it is Vy. Vy over 4. So therefore, you can just say Vy equals 4 meters per second times cosine 32 degrees. So somebody, let's see.
PK.
PK, you there? PK's not with us today.
Synod.
Jack, Senate,
What?
what'd you get for this, for VY?
Still typing it in.
So cosine 32 times 4 meters per second. I'll come back. You can confirm.
Elizabeth.
Elizabeth, what'd you get for this? So everybody calculated. I might call on you.
3.39.
3.39. Elizabeth, can you confirm that?
Yeah.
All right. So the y component there is 3.39, and to get the x component, this is going to be negative. It's going to be to the left. So Vx is just going to be sine of 32 times 4, or 4 meters per second times sine of 32. Everybody do that, and I'll pick somebody first.
Thomas 2.
Thomas 2? Are there 2 Thomases? I must have just imported your name, and it calls you Thomas 2. So what'd you get for that?
Working on it.
And while you're working on that, I'll start drawing on this
I
one.
got 2.12.
2.12. And
Cassie.
Cassie, can you confirm that? Cassie there? No Cassie?
Rajan.
Rajan? All right, in here, can anybody confirm it? Okay, all right, so we're good. 2.2 meters per second. So we've got this, I'm not gonna write it again, 3.39, 2.12, and that should actually be negative, but I'll deal with the negative in just a second. So this is, and I realize this is kind of a mess, but I'll try to clean it up in a little while. So this vector, I could do it this way. I could say, here's the y component, here's the x component, or I could go over and do the x first, which I think I will, just for the heck of it. No, I'm not going to do that because I know that angle. So it's better to draw it this way. So here's the y component, here's the x component. So in this case, Vy is going to be 6 meters per second times what? Cosine or sine of 10? Anyone? Cosine of 10. So calculate that out for me. Garrett. 5.91. And
Iris.
Iris, can you confirm that? Is this 5.91?
One sec.
You got something different?
No, I just haven't plugged it in yet.
Oh, I can't hear you, Iris.
Yes.
Hold on for a second. Maybe there's something wrong with my speaker.
Yeah, I got the same thing.
Yeah, the speakers seem to not be working. Oh, it's because I've got this muted. Hold on for a second. I'll switch it so you can talk through my computer. It's not working either. Oh, crud. All right, Iris, just give me a thumbs up. Is that right? Okay, good enough. I've got the projector muted, and you're speaking through the projector, so I can't hear you. All right, so now I need Vx, and that's going to be 6 meters per second times the sine of 10. This is a nice pen. Let's see who I got there.
Thomas.
Oh, somebody different.
David.
David. Oh, David. In the chat, tell me what this number is. $1.04?
Abby.
Did you get 1.04? All right, 1.04. All right, so time to bring all this together, and I'll try to make this a little bit more organized. So I need a table, just like we've had before. Nice table. X components, Y components. And I want my two component vectors here, and they're going to add up to the resultant vector there. So I could put them in either order. The one component vector is the cart heading, speed, or heading and speedometer reading. I could write that here. I'll write it first. Cart, heading, and speedometer. I don't have any information for that though, so this has got to be blank. This is the thing we're looking for. That's the unknown that we're missing. The other component of that is the aircraft carrier velocity. Aircraft carrier velocity. And for the aircraft carrier velocity, that's this. So it's 6 meters per second, 10 degrees east of north, but I've broken that down into the y component and the x component. And I just want to look at my graph really and make sure that neither of these needs to be negative. This is up, so that's positive. This is over to the right, so that's positive. So the x component is positive 1.04, and the y component is positive 5.91. And so put it in the wrong place. 1.04, 5.91. That's the aircraft carrier. And then finally, these two component vectors add up to the resultant. And this is the cart actual velocity relative to the Earth. When you're solving one of these problems, you don't have to have all this notation. I'm just trying to emphasize that this is always going to be the resultant. Whoever the star of the problem is, if that's velocity relative to the Earth, that's what we're looking for. These are going to add up to that. So the y component of that is positive 3.39, but the x component's to the left, negative 2.12. So this should be 3.39, negative 2.12, and exactly. So this plus this equals that. So how do I get this? Subtract. So anybody can actually, Jack Giuliani, will you tell me what's this? What's 3.39 minus 1.04?
2.35.
2.35. Can somebody check and just, yeah, okay. And what's negative 2.12 minus 5.91? Anybody? Negative 8.03? So really, I've got the answer now. It's just that there's this other step where I've got to take that and actually turn that into a magnitude and a direction. So to do that, I'm back to, so the grid again. And I know I'm saying X and Y here, and on my grid that I'm drawing, I'm gonna write north, south, east, and west, but hopefully you've got that kind of flexibility. So taking this number, the cart speed and heading, this is positive 2.35. So I go this way, 2.35. And then I go down 8.03. Huh. I think this is a different answer than when I did this before. I don't know if I was wrong that time or I'm wrong this time. Has anybody seen something that it was?
I didn't get those two answers when I plugged it in.
You didn't
The
get?
green.
You didn't get these?
Yeah.
Well, let me check these. So the usual mistake, if you're going to have a mistake there, a lot of people are in radian mode. So let me do 10 cosine times 6. I get 5.91. That's good. And 10 sine times 6. 1.04. And you know, maybe I just did use different numbers before.
Yeah, I was
So it might be
radians.
how you put it in the table with the x and y. I can't tell the split, but it looks like different than mine.
So let me check. Maybe I made a mistake there. The so on this one, this is the
Yeah, because you even say dy is 3.39, but you put it into the x.
Wait, are you subtracting, not adding?
3.3. Oh, that's it. Yes. So if you look back over here, this is the resultant vector. This is the velocity of the golf cart relative to the Earth. So the x component of that was negative 2.12, and the y component was 3.39. And yeah, I switched those. So we got to redo the math. All right. So then these are wrong. Can somebody do this one and then somebody else do that one? Negative 2.12 minus 1.04, 3.16, and
2.25.
2 point,
Negative 5.2.
yeah, negative.
Negative 2.52.
All right. So that, yeah, that's more in the range of, I think, what I remember getting. So, need to redraw this. So this should be, and by the way, if you make a mistake like that on the test, and I can see your work over here, and then you just wrote it down wrong, I'm going to take off very little for that, if anything at all. If that was the only thing you did on the test, I probably wouldn't even take a point off.
This isn't on the test, right?
No, no. But just in the future, just so you know, I mean, I do this kind of stuff. It's not that I don't know how to do it. I'm just being a little careless. And all I really care is that you know how to do it. So x is negative 3.16. So that should be 3.16 this way. And then y is negative 2.52. And then this is what we're looking for. So for the magnitude, that's just going to be the square root of 3.16 squared plus 2.52 squared. Can somebody do that one? I won't call on anybody, just somebody crank it out.
16 plus 3, 4.
Take the square root,
You have to take the square root, so it's around 4.
around 4. Precisely is exactly, should I, 4 or?
It is 4.04.
4.04. Yeah, that's what I got before when I did this. 4.0 meters per second. So that's the magnitude. And then I've got to have the direction. So this direction would make the most, let me draw it in. It's kind of hard to see for the people at home. This direction would make the most sense if I were to describe this angle. So west would be this way. I'm going to say it's so many degrees south of west, whatever that angle ends up being. And if I call that angle theta, then theta equals the inverse tangent of this, write it over here, this over this. Tangent is opposite over adjacent, so the inverse tangent of the opposite over the adjacent gives you the angle. And that should be 38.6, or at least that's what I got before. Can somebody check that and see if... So the answer, the final answer to this question is, if you are in a golf cart and you want to go in this direction at that speed, and you're on an aircraft carrier that's moving in this direction at that speed, what you have to do is point your golf cart in this direction according to your compass and keep the speedometer on that. So we write the final answer, 38.6 degrees south of west. So there's a homework assignment tonight where you have to do 2 river problems. The first one's not too bad. The second one is this kind of thing. It's pretty involved. So, but it's just 2 problems. Anybody have any questions? Nobody ever has questions. It's almost a worthless thing to say, but just in case anybody has a question, I want to ask you. All right. Now I want to give people a chance to ask about the homework if you have any questions about that, and then we'll talk about the test. So, didn't mean to go there. Does anybody have questions about the homework? There were the classic river problem, and then there was the still more river problems number 2. Open up the classic river problem. Turned out that Jane's way was faster. It only took 35.7 seconds, and Bob's took 40.3. But do you want any explanation for that? And then the other one, oh, you can't see. The other one was number 2 here. And I think this was a lot more straightforward. The one thing I want to point out is that, and well, first I'm going to make sure that the volume's working again with these other people. All right. We can hear you all now if you need to talk. So one thing I want to point out is that if you're just trying to find out something like the amount of time it takes to get across a river, if this resultant vector represents how fast the boat is really moving, you don't have to figure out what this distance is and what that speed is and then divide distance by speed to get time. Since this dimension and this dimension are independent from one another, if you want to know how long it takes to get across the river, then you only need to know the velocity in that dimension. So the 4 meters per second, that's all we need to figure out the time it takes to get across the river, that and the width of the river. This component is going to tell us how far we move up the river during an amount of time. So a lot of people feel like they need to calculate what that distance is in order to get the time, but you don't. You could do it that way, but it's extra work for you. Any questions? If you have any, just bring me back to whatever you want to talk about. So I have the test in my notebook here, and I'm going to look at it, and this is the test from first term. I think I'm probably going to change it around a bit. Please don't talk to anybody from first term and get their tests and copy the answers, but just in case that does happen, I want to make sure this is not the same test. But it'll be pretty similar. So the first 2 questions, can you all hear me? Okay. First 2 questions are going to be one of those questions like, let me put myself back up here. It's going to be, describe an example of a motion that has positive acceleration and negative velocity, or positive velocity and negative acceleration, or positive acceleration and positive velocity. And you're going to need to say something like, you could give a specific example. You could say if it's an object that has negative acceleration and 0 velocity, it could be this pin at its highest point. So when it gets to the top, it's accelerating downward, but it has 0 velocity because it's stopped up there. You could give an easier kind of answer. You could say 0 velocity and negative acceleration would just be when you're not moving, but you're starting to move downward. So acceleration means increasing in speed in a certain direction, and velocity just means how fast you're going. So there are going to be 2 questions like that, and you can attack the 2 halves separately. You can say, like, for example, on last year's test or on the first term test, the first question was, describe an example of a motion that has negative acceleration and negative velocity. What would you say there? Mm-hmm. So which way is it moving? So it could be moving left, that's negative velocity. And if it's accelerating negatively and moving negatively, is it going to speed up or slow down?
Slow down.
It's actually going to speed up.
Speed up.
So it's accelerating in the same direction that it's already moving. Numerically, that you could just say, for example, that the velocity is -2, and if you have negative acceleration, you're going to be subtracting something from that every second. So -3, -4. Positive acceleration just means speeding up in that direction. So if I have something with negative acceleration and negative velocity and positive acceleration, what's it going to be doing? Going left. Negative velocity is easy. It's going left, but what's it doing? It's accelerating to the right. Yeah, it's slowing down. And eventually it's going to stop and it's going to come back to the right. Yeah.
For this problem, could we like draw like a picture? Could we draw like a car and like?
Yeah, you could, but you've also got to use words. So do some explaining.
So it's like acceleration has direction, essentially.
Yeah.
Okay.
Yeah, acceleration is just it's what are you doing to the to velocity every second. Let's see. I don't know why I felt the need to get back to my website. So there are 2 questions like that, and then there are going to be a few multiple choices, and a lot of the multiple choices are going to be trying to see if you really understand the difference between acceleration, like positive acceleration, negative acceleration, positive velocity, negative velocity, constant velocity, really teasing those definitions apart. Then there are going to be some graphs, and instead of having to draw the graphs, you're going to be matching them. I did a warm-up last term that I think I didn't give you, but I can show you that now. It would be an example of this. Right here. So, match each position versus, this is very much like what's on the test, except not exactly. Match each position versus time graph with the correct velocity and acceleration graph. So this is position versus time, and so first of all, these are velocity graphs. Which velocity graph goes with this position versus time graph? Think about it for a second. And then which acceleration graph would go with it? So just don't say anything for a while, but think about it. So this is position graph. These are the velocity graphs you can choose from. These are the acceleration graphs you can choose from. In case you can't see very well, this is 0. So here we've got constant positive acceleration. This is 0, so there's no acceleration. This is 0, so in this one, this is negative acceleration. And then with velocity, these two, this is 0, so we've got positive constant velocity, and then 0's up here, so this is negative constant velocity.
On the test, are there going to be any like curved velocities, or are they going to all be straight?
No curved velocities.
They're going to be curved acceleration.
So there could be curved position graphs, but there can be curved position graphs or linear position graphs. There can be linear tilted or level velocity graphs, but you won't have any tilted acceleration graphs. So it'll always be constant acceleration.
Okay.
Either constant positive or constant negative. All right, so which velocity graph is this first position graph? B, yeah. So it's got constant positive slope, which means constant positive velocity. And if there's constant velocity, what kind of acceleration is there? None. No acceleration. So it's going to be 0. So the slope of this gives us this, and the slope of this gives us that. So let's skip to this third one here. Think about that one for a second. Which velocity graph, which acceleration graph would match with this position graph over here? So here we've got steep positive, A and C. Steep positive slope going down to no slope. So that would be a big positive velocity going down to 0 velocity. And now the slope of this is negative and the same the whole time. So acceleration's negative and the same. Or another way to look at it is we're losing velocity at a constant rate, so this has got to be negative. So that's the kind of thing. There are going to be 4 questions like that.
You're gonna have to like work backwards, like acceleration.
Hey,
How are ya?
all right, how are you?
Well. Oh, you have to work backwards, like acceleration.
Yeah, well, yes. So the question Christina just asked is, are you going to have to work backwards? So it won't be exactly like this. I may say which position graph goes with acceleration graph B.
Well, wouldn't it be a crystalline velocity?
Yeah, so acceleration graph B where there's no acceleration, it could be either this or that. So that wouldn't really be a good question. But I could definitely give you this one. I could say which position graph is like acceleration graph A, and that would be the second, the upward curve. So you may have to work backward. Looking on the next page, there are several questions seeing if you know the difference between displacement, distance, speed, and velocity. So if you remember back to one of those practice tests, there was some question about driving from Burlington to Montpelier and back. If you do that, what's your average velocity? 0. Because velocity is displacement over time. So your average speed is going to be different because speed is distance over time. And your distance is the distance there plus the distance back, whereas your displacement is just final position minus initial. So there are going to be a few like that. Some questions asking you about balls thrown up in the air. So you throw something up in the air, what happens to the acceleration? So when this is up in the air, what's happening to its acceleration?
It's a constant negative 9.8.
Yeah, nothing happens to it. As soon as it leaves my hand, the acceleration is negative 9.8, and it stays negative 9.8 the whole time. Does the speed change? Yeah, the speed gets slower, and then it gets faster again. The velocity, does the velocity change?
No,
Remember, it's like, if you catch it in the same spot.
Yeah.
So acceleration is,
Well, I was just
Sam?
gonna say, like, it depends on the moment in time. Like, at certain moments in time, it'll be different, but at the end, it'll be the same.
the velocity will be?
Yeah,
Well, when I'm holding it, if I'm holding it now,
yeah.
and I'm holding it again, the velocity is the same. But
Yeah.
the moment it leaves my hand, what kind of velocity does it have? Positive or negative?
Positive.
Positive. And it's a high positive velocity.
Yeah.
And then it stays positive until it gets to the top. And what's the velocity there?
0.
0. And then what happens to velocity? Negative. So the velocity, because the acceleration is negative 9.8 the whole time, that means the velocity is always changing. When it's not touching my hand, it's always, every second it loses 9.8 meters per second. So that's kind of tricky stuff. Just that diagram, there's one diagram somewhere in the notes, I think, that shows a ball going up, and we're figuring out height and time, and that would be a good thing to go back over. There's going to be one graph where I'll describe an event or something that's happening, and you have to graph acceleration versus time. So some of them in class I've done with you, or a ball bouncing. I could go back through some of the warm-ups that we've done. Let's see. They won't necessarily. There was this one about the Nerf dart. When a Nerf dart shot out of here and it hits a screen or a wall, like, graph the acceleration from the moment it starts to move until the moment it stops. Oh, this warm-up is very much like questions 1 and 2. Like describe a motion that would have negative velocity, positive acceleration. These are all the different possibilities for that. So there's going to be a graph. There's going to be one unit conversion, and I'm going to start with a rate. It's going to be so many things per hour or so many things per second, and you have to convert that to some other rate. And I'll give you everything you need to know, except maybe not hours in a day, but if you need to know things like hours in a day, you can ask me.
Like you went to
Yeah, it's really obvious kind of stuff. Then there are going to be 4 problems. For the problems, you're going to need the formulas, and the formulas, they're on my website right here. This is all you need. And there's that Quizlet to help you study, and if you just memorize these, remember I'll give you an extra 3% added onto your test.
Well, you like to see it there at first.
Yeah, so I was telling, I think, the other class that you all said, can I check them and then confirm? So what I'll do is, if you want me to look at them and tell you if they're right, I will, but you only get 2%. If you're totally confident in yourself and you don't need the checking, then you get 3%.
Because if we're wrong, you can just give us the formula.
Is there a scale on the test?
If you're wrong, yeah, I'll give you the formulas. You don't get any multiple choice
said
or
you get 3.
any extra credit.
Or does it like block off at 100%?
I can give you extra credit. It's just I think at the end of the class, it's not going to go on your GPA that's over 100%. But yeah, you can have 103%, 104% in the class. And in Power School, it shows up. There's no scale. No scale. But you get to take it again. So if you miss any of these, there's going to be another version of this test with comparable kinds of questions. Not the same exactly, but over the same stuff.
Did you do the whole thing or just the thing?
No, with this one, there are 3 sections. There's kind of the multiple choice short answer section, and then there's the problem section, and then there's the extended problem section. So you do have to do the whole section over. So with the problems, those are the kinds of formulas you'll need. Looking at the problem, looking at my solutions to this last test, there were no questions that required more than one problem. Or sorry, no more than one formula. But then there's going to be the extended problem where you're going to need to use a lot of different formulas. And the extended problem has, it had 5 parts last time, and each part was worth 2 points, so that's 10 points. So point-wise, 10 points for the extended problem section, 18 points for the problems. There's a 2-point conversion one, and then 4 regular physics problems, 4 points each, so that's 18. And then it looks like I actually broke this up into 4 sections. So the first, I can't remember if the first page and the second page went together. But the first page is 9 points, second page is 8 points, 45 points altogether. That has no bearing on how much this counts ultimately. That's just, if you get 45 points, it's 100%. And it'll count as much as your next test, regardless of how many points are on that. Any other questions? All right, I feel like I've sucked the life out of you, so you need to go feed or something.
Wait, if we don't memorize the formulas, do you give them to us?
Yeah, I'll give you a little sheet of paper that looks just like this.
Okay.
I'll have a pile of them on the desk when you come in. And then I'll start walking around. And for the remote people, you can just, I have everybody sign the honor pledge this year, just since school is sort of flexible and some people are here and some people aren't, and it would be a great time to cheat. I at least want people to write on your test, on my honor, I have neither given nor received any aid on this test, and then you sign it. And that makes me feel a little bit better that people are being more honest. I think first term people were pretty honest. Please don't cheat. I give you every chance you can take it again. I'll help you. I really want you to get it right, but just don't cheat. Does anybody have questions, concerns, anything you want to complain about? At me, other people?
I don't like your no cheating policy.